In the past couple of videos, I have hounded you over the formation of enamines and amines. Now, I really do have to do some clear-up work, get you out of the mud a little bit, and kind of talk more about these amines especially. So these are the compounds that have a carbon double bond nitrogen. All right, now, here's the story with these particular types of functional groups. Over the course of time in organic, whether you were taking chemistry 251 or 252, what you saw almost every single time when a nitrogen was concerned was a nitrogen with 3 bonds and a set of electrons. This was the most stable form of nitrogen. We said that this gives nitrogen a formal charge of 0, and the reason is because nitrogen has 5 valence electrons, and we take 1 away from every bond that it makes, and then we take 1 from each dot that we draw, which represents an electron. So 5 minus 3 minus 2 is 0. So this gives us a formal charge of 0, which makes nitrogen very, very happy, right? So in other words, this was a nitrogen maybe attached to a carbon, and it could have a hydrogen here and a hydrogen there, forming an NH2. Well, what we saw with amines were something a little bit different. We saw a nitrogen that was double bonded to a carbon. And almost in every single case, it was also attached to something else. So this does not mess with the formal charge, folks. It's still 3 bonds in total. It's still a set of electrons. We still have a formal charge of 0. That's not what I'm getting ready to tell you. What I'm getting ready to tell you, though, are bond angles. Remember back in chemistry 251 when we were talking about bond angles and tetrahedrals and 109.5s and 120s and all the other ones that came around? Well, we said that certain atoms have bonds, bond angles, bond lengths that are appropriate for that particular atom. So the story here is that this double bond to carbon puts a little bit of strain, folks, on that nitrogen-containing group. And because of that, these have a tendency to react, and these have a tendency to do things for us quite easily. So I can kind of say that amines are going to be pretty reactive for us. They are very good intermediates. Intermediates basically means the middleman before we get to what we actually need. All right, so let me give you an example. Let's say that we have a carbon double bond oxygen with a CH2, CH3, and a CH2 and a CH3. And let's just react this with something simple like ammonia. That's all that we have to do. Oh no, ammonia, what do you mean? We've not done an example. Yeah, we have, because I need you to think of this almost like an NH2 and a H. That's what I need you to think of this group as. So under this reaction, we have a type 2 carbonyl. That type 2 carbonyl is a ketone. That ketone is going to react with ammonia, which is NH3. And we're going to see the amine formation that begins to happen here, just like we've always done. So what will go on is that this carbon double bond O, and here is the ethyl group, and there is the ethyl group on the other side. We can take our eraser and get rid of it and then replace that with a nitrogen. And that nitrogen needs 1 more bond, and that 1 more bond will come from an H. The other 2 hydrogens that it has here in total can actually go away, pair up with the oxygen in order to make water. So this is the amine. This is the same type of examples that we've always done before in the past. There's no difference in what we just did. So that nitrogen has 3 bonds in total. 1 of them is a double bond to a carbon. We now know that amines, it's not really particular fond of that kind of position that it's in. You're putting some strain on it. Think of it as, super hot yoga. So this molecule will love to break down if it can. And we can simply do this by adding something like H2. Just H2. Now, if you go back and think about what H2 did back in Chemistry 251, we added hydrogen, and that hydrogen broke the double bond, and 2 hydrogens went on, one to the carbon and one to the other carbon during that time when we discussed them. Well, folks, the same thing's going to happen here. So if I take this molecule, and this is now a nitrogen with a hydrogen on it, and I've got my ethyl group on this side, and I have my ethyl group over here, we can take H2 and palladium, just like we did in Orgo 1, and I can take my eraser and break the double bond because we know they're reactive, and hydrogen goes on to one side, which makes that a CH at this point, and then hydrogen can go to the other side, which makes that now a NH2. And this is the formation of a straightforward amine. So we have taken a top 2 carbonyl, a ketone. We've reacted it with ammonia, pretty easy to get in a laboratory or on a consumer shelf. We have formed an imine in the middle. And then if we hydrogenate it and put some hydrogen into the system, we can destroy that double bond because it's not very stable, and we can put a hydrogen on each side of that double bond. And this will help us form a amine in the process of that. All right, now let me kind of do another example. Maybe I need to go back and take a look at maybe some of those derivatives that we did that we ended our last video on. So let's take this ketone, and this ketone again, I'm just going to draw 2 ethyl groups on either side of it, on both sides. And then here we'll do a NH2, and that NH2 is connected to an OH. And we want to know what would form from this reaction. You do it just like we did it and how we ended in the last video. You look at this molecule and you'll go, okay, well, we know that this nitrogen is a bully, and that nitrogen's going to come in and that oxygen away. And then we have a nitrogen that will go on in this spot, but that nitrogen is bringing some buddies to the club, and that buddy is a OH group. All right, so this is the formation of the oxime that we have discussed prior. And then at that point, this is kind of where we stopped. And we said, well, this is an amine, and this is the functional group of an amine, and this is what it looks like, and this is how you draw the structure. But we never really went further. Now you know that these things are not very stable because it's a carbon double bond in. So these molecules will love to react, and they will react with something like H2 and palladium, again, that we used in Orgo 1. So you can assume that what happened prior is going to happen again. So this is a double bond NH, and off of that carbon are 2 ethyl groups, and that hydrogen will target that double bond just like it always has, and it will get rid of the double bond, and hydrogen goes on to one side and hydrogen goes on to the other. So folks, there you go. That is the destruction of the imine bond in order to form again another amine group. So NH2 is what's going to go on here. Now, I know what you're saying. Well, wait a minute. This is a nitrogen and there's an OH that's there. So why didn't you just keep the OH there? Okay, well, if that was the case, then we would have had to have drawn both of these like this, right? So this nitrogen is going to have a bond to a carbon, a bond to an OH, a bond to a hydrogen, and folks, this OH group, it can be protonated. And it's going to look for a proton, and that proton we have put into the system, that proton is in the form of H2. So we actually see a complete destruction of that OH bond because of that. So just a little bit more advanced type of thing. However, we end up with the same product, and that same product is going to be right here, and that is the NH2 group that's going to be on that particular type of carbon, all right, or nitrogen. So these are the stories with amine. Again, they're not very stable. We can react them with H2 and palladium, and really pretty much any type of amine that we have will end up with a NH2 onto that carbon almost every single time, all right? So we call this a special term, and this is called reductive. Remember, Madonna, Lady Gaga, reductive version of one or the other. So this is reductive, meaning that it's reducing the number of bonds. We've seen this with carbon to oxygen bonds, but we can also refer to reductive in carbon to nitrogen terms as well. So we are seeing a double bond here between carbon to nitrogen, and we are reducing that to one bond between the carbon and nitrogen, and we are reducing it, so therefore we can call it reductive because we're reducing it. That's what that basically means. And then the final term that we're going to add on to this is called amination, not animation. Animation is Disney, okay? Animation is not organic. Amination is organic. So amination, you can see the word amine, and amine means NH2. So reductive amination basically means we are reducing, reductive, the number of carbon to nitrogen bonds in order to make an amine, which is the animation part or amination part of this reaction. So reductive amination, that is the term that we use for these types of reactions, okay? All right, something else that I want to talk about with aldehydes and ketones as far as reactions go. So aldehydes and ketones can also react with water. Okay, this is another reaction that we tend to talk about in this field. The reason is because we see it quite often. It is a pretty common reaction in a laboratory, so therefore we want to at least give credit where credit's due and kind of show you an example of it and kind of tell you a little bit about what happens when water reacts with an aldehyde or ketone. The products here, the products are going to be called hydrates, and you probably have heard of a hydrate in General Chemistry 1, but the definition of hydrate is a little different in organic than it is in general chemistry. So in general chemistry, a hydrate was anything that carried a water molecule with it. So you often saw this little dot at the end of a formula, and that dot probably had a big coefficient in front. It could have had a 2H2O, a 5H2O, an HH2O, a 10H2O. It could have had a number of different things there. So if that's the case, that's great, not a problem. However, that hydrate definition is something a little different in organic. So what we are going to be referring to as hydrates in organic reactions, especially with aldehydes and ketones, are molecules with two OH groups on the same carbon. All right, so let me give you an example here. This is how it's different. Let's say that I have a carbon chain that goes down like this. And off of this carbon chain, let's say that I've got maybe an OH here and maybe an OH there. Well, those OH groups are on the same carbon, and there's two of them. So we're going to refer to this as a hydrate. It is a molecule with two OH groups onto the same carbon. Now, you can kind of imagine what's going to happen here, right? If this is the product that we're after, and this is the product that we're focused on in this lecture video, you can probably imagine that one of these OHs was probably a double bond O at some point in time. And there's my ketone piece, right? Or my aldehyde piece. And if that double bond's destroyed and we add a hydrogen onto that oxygen, then we can get an OH group over there on the right-hand side. Okay, well, that also means that this carbon now has 5 bonds. It's probably not going to work, and that was probably an incoming nucleophile right here, this OH group. And this OH group could have came from something like water. Keep in mind, there is the H and the OH piece. So what basically I'm telling you is that we can take an aldehyde or a ketone, either one, And here's just an example of one of them, right? And I can add water to this. And there's the OH piece that can add on as a nucleophile. Well, when this carbon double bond O breaks, remember, we said that that oxygen will temporarily get a negative charge. And it's going to look for something that it can pull a proton with at least in order to satisfy that. Because when this goes back, this carbon's going to say, no, 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 you already messed it up. So you're going to have to deal with the consequences, and you're going to have to keep those electrons. I'm sorry, I'm not going to get rid of anything. There's nothing for me to get rid of. Okay, well, look, water is going to be that supplier. So this H can come around, and it can help satisfy that oxygen-containing piece once it becomes negative. Now, is that really how the mechanism works? There's more to the story than that, but this is a very good way to at least introduce you to this reaction of water with an aldehyde or a ketone. So let me kind of clean this up a little bit. We're going to take a aldehyde or a ketone, and again, I'm going to put R or an H there to represent one or the other. We are going to react this with water, and what we end up with as a product is a carbon. Here is the R group. Here is the R group or the hydrogen. So this oxygen comes in for the kill. Blink! There it goes. That's where the nucleophile goes. And then this carbon says, oh no, I've got too many bonds. You're going to have to take one of them, oxygen. And it shoves those electrons up to O. And oxygen takes these electrons and says, oh no, I'm negative, I want to push them back. And it tries to push them back, and carbon says, nope, sorry, no way, no how. And then the hydrogen from the water molecule will go on to that oxygen to form another OH group. All right? So here we have a carbon. That carbon has two OH groups on it. They are basically twins in a way, and we call these a hydrate. All right? So that's basically how we can form or react these aldehydes or ketones with something as simple as water. Now, we also have another name that these can go by. Instead of a hydrate, back in Chemistry 251, we used this term geminal. I don't know if you remember it or not, but we use the term geminal almost like in terms of Gemini twins. And here we can bring that back. So we can call this a gem for Gemini twins, diol, gem diols. So the gem is representing same, and diol means two OH groups. So gem diol is another name that we can use instead of hydrate. All right? Okay, so let me give you a couple of real examples here, and we'll go through and just kind of do them one by one. You see that these are pretty easy as well compared to everything else that we've been doing. So let's take C double bond O, and we'll do a methyl group on each side. So this is acetone, and acetone will react with water, and this is going to form a product, and that product is going to be a carbon, and then there's the methyl, there's the methyl, here's the OH group from the water, there's the destruction of the double bond, and the H from the water is going to go there. So folks, we can go through and we can actually name this using the alcohol nomenclature that we learned at the beginning of the semester. So this is a 3-carbon long chain, and that is called a propane. Drop the E, and then we're going to add diol because there's 2 alcohol groups, and these alcohol groups are at carbon number 2 and at carbon number 2. So 2,2-propanediol is going to be the name. Now, did I have to put a hyphen there? No, you can squeeze them all together if that's what you want to do. That's perfectly fine. I don't care. But if you do that, you probably would want to keep the E at the end and call it propanediol. That's probably a little bit more appropriate. It makes it look a little bit better and not as strange to bump the N and the D side by side. All right. Something else I want you to pick up on is that this double or this arrow that reacts, that takes my reactants and connects them to my products, is double barbed. So basically what that means is that it's equilibria. So we have the formation of the product and we have the destruction of the product that goes back to the reagent, and this is at equilibria and it goes back and forth, back and forth, back and forth. All right, so that is a little bit of Gen Chem 2 type of lecture material that is built into this as well. All right, this works for aldehydes just like it works for ketones. So I can do a C double bond O and an H and a methyl group on this side. I can react this thing with water. I can get some products that form with it. So here is my carbon, and my screen went a little happy. So let me clean this up. Look at that, how awful and messy that is. All right, so carbon, double bond O, and then a methyl, and then a hydrogen. And this water molecule, again, you want to look at as H and OH. So this OH group is the nucleophile. Zoom, it goes in, attacks the carbon. In order for carbon to take that OH group, carbon now has 5 bonds, and it can't have 5 bonds. So carbon now looks at that oxygen and says, sorry, you're going to have to take those electrons. You wanted them anyway. You're the one who caused all this mess. And that oxygen gets those free pairs. So when the oxygen gets the free pairs, it freaks out on us and it says, I don't want the negative. I'm sorry. I should have never done it. And carbon says, sorry, you made the choice. You made the decision. You got to deal with it. I'm a top 2 carbonyl. I don't really have anything that I can get rid of. Sorry. And then the oxygen takes the hydrogen that is from the water. And this goes back and forth, 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 back and forth. I mean, that's exactly what it does. The problem here, though, is that sometimes the reagents are actually more preferred over the products. And you got to keep in mind that oxygen does want to shove the electrons back, and carbon does have to make a decision on whether or not to accept those electrons back. And if it has a good leaving group, then that leaving group can go away. And folks, this incoming bond right here, this OH group, this can easily become protonated. And if it does become protonated, then that water molecule is going to leave, just like we discussed very early on in the semester with the alcohol reactions. So if that's what goes on, we do get a reversion of the reaction, and it goes back to the reagent side of the house on us. Now, you're probably wondering, well, how on earth would this get protonated? I'm not putting it in acid, am I? Well, no, you're not. But where did this hydrogen come from up here at the top? Well, it had to come from somewhere. It had to come from a source. Well, that hydrogen could be the same hydrogen that could target this one down here. So this is basically just statistics. Which OH group or the O group is the hydrogen going to land on first? Because if it lands on the OH that is already there, that was the incoming nucleophile, then this is just going to protonate the alcohol group, and that group's going to leave. So oxygen can shove the electrons down and redraw the double bond and go back to the way times were when things were good for it. So if that is what goes on, that is what's causing the reversion of the reaction back to the reactant side of the house. All right. So some aldehydes, some ketones react with water better than others. It really depends on the structure. It depends on how big the structure is. It depends on what is there. But you need to understand that these reactions do have a tendency to go backward, and they have a tendency to actually maybe not even react at all. Okay, so we can show them. We can show the product formation. We can say it's there. We can say that it's temporarily there at least. But at the same time, we also have to have our minds open, and we have to accept the fact that maybe some of these will not do a reaction, meaning that they do form the products. We do get a reaction. We do get product formation. But once this product forms, it goes back to the left-hand side, and it completely destroys itself, and this reaction will stay so far over on the left-hand side that we form extremely, sometimes, tiny amounts of these products. And sometimes they're so tiny that we can't even recover them. We can't even obtain them in the lab because the amount is such a small amount. So too small to detect, we basically say no reaction. Because what's the major product? If the product is here and there's not enough of it for me to obtain it, well, I can't really say that a reaction went forward, can I? Because I'm going to end up with basically this molecule over here to the left. Same story with the ketones up here. Don't get confused. Ketones and aldehydes are the same way. So this ketone can react with water to form this product, but this product could be in such a tiny, tiny amount that I cannot recover it from a lab. I cannot recover it from a reaction because once this forms, it can simply revert back on itself and give me the ketone back, and I will have the majority of the ketone in my flask or container or whatever I decide to use it with. All right. So that's the story with the additions of water and as far as the hydrates are concerned. And again, we're talking about hydrates, meaning molecules with two OH groups. All right. Something else that I want to talk about hydrates. What you see on the screen right now is basically at the very bottom, different examples of hydrate compounds. And what you're seeing is that the first one has an OH and an OH, and this carbon has a R group here and an R group there. And then this OH and that OH are on a carbon that has an R group and a hydrogen here. And then here we see an OH and an OH, and this carbon has a hydrogen there and a hydrogen there. And look at the stability of these things, all right? So the least stable of the bunch is actually going to be the more substituted ones. So here we see two OH groups onto a carbon that has a R group and that has a R group. These take up space. And the OH groups take up space as well. They're quite large. They have a large electron cloud on them. They're both negative areas. They push each other apart. So because of that, there's significant amount of strain that can happen here. When the two OH groups go onto a carbon that has one of those replaced with a hydrogen, there's a little bit more room. So think of this as a subdivision, right? Two OHs move into a subdivision. There's an empty lot on one side. Both of these OHs are going to be a little bit happier because of that, and because of that they are also a little bit more stable as far as a compound's concerned. And then finally here is a carbon that has basically moved into a new subdivision. So we have an empty lot on the left and an empty lot on the right, and because of that these OHs are not bad neighbors because they're across the street from each other and they are not basically butted up side by side against other people where they have no privacy. So there's more room to move around. There's more room to go out and explore and play around. And because of that, it makes those OHs much happier. And because of that, we have a more stable gem diol or a hydrate because of that. All right, so that's where this video is going to stop. In the next one, I'm going to pick up with this same topic, but instead of water, we're going to be using alcohol because that's something that we did in Chemistry 251. We talked about reactions with water and reactions with alcohol because we saw that they were very, very similar. So in the next video, we'll pick up from that. We are almost done though, so don't weird out on me yet. There's still a few topics that are out there in Type 2 world, and I just need to bear with me just for a couple of more videos for us to get through it. So almost finished, but still just a couple of reactions on our dinner plate.